Hello fellow problem solvers. So today we're going to be talking about the principle of mathematical induction. The goal here is to introduce the topic of mathematical induction first by building up the intuition that will help you understand the concept. And the way we're going to be doing that is by problem solving. Namely, we're going to be solving the problem with tiles and a missing square. So the setup is, you have a 2 to the n times 2 to the n board with one 1 times 1 square missing from it. Your goal is to show that you can tile this board with the L figures that you see on the screen. You can rotate these figures any way you like. The only condition is that no two L shapes overlap and that every L shape is both completely inside the board and covers exactly 3 of the squares. How would you do this? So the first problem strategy to use in these types of problems is to play with the problem with small values at the beginning. Now, if you haven't done so, I'd invite you to pause for 5-10 minutes and play with small cases. And I promise we'll talk about induction after we finish this problem. Now, for n equals 1, things are pretty simple. We have only one L tile that we can put one way and we are done. Now for n equals 2, it's a bit trickier, but we can still manage. Now notice that in each case, we had to place one of our L tiles around the missing square, and if you solved it sequentially like I did, you first place that tile, and then you put the other tiles. And in each case, you put them into this larger L shape. Now, if you divide the board into 4 equal pieces, what you're doing is, you first tile one of the pieces, and then you try tiling an L piece that had twice the size of our L piece. So now, when we go to n equals 3, do you see a quick way of tiling this figure? Well, if you divide them into 4 equal parts, you see that you've already tiled one of them in n equals 2. And now you're left with an L piece that's 4 times the size of the tile. Now, how do you tile this? Is there something you know from n equals 2 that can help you finish this? Well, this L piece is twice the size of our n equals 2 L piece. So this can be tiled by 4 n equals 2 L pieces in the same way we did it before. And then those can each individually be tiled just like we did it before. Now before we go on to n equals 4, take a moment to put together what just happened. We divided the board into 4 equal pieces. One of them we knew how to tile from before. After we tiled that, when left with our L piece, we divided it again into 4 smaller L pieces that we already knew how to tile. And with this, we finished the problem. And now, do you have enough information to tile n equals 4? Here's an example animation for n equals 4. And now with this in mind, can you now tile n equals 5, n equals 6, or n equals 7? Could you tile a 128 by 128 board? And chances are you're getting a hang of this process. Now my question for you is, how are you able to do this? One answer is that you're using facts you've previously uncovered. When you wanted to tile a 16x16 board with 1 square missing, you're using the fact that you know how to tile an 8x8 board with 1 square missing. And then you're using the fact that you know how to tile an L shape with length 8 to tile an L shape with length 16. What you're doing is you're building up your knowledge of things you've already done to do bigger things. And now that you've proved you can do this in specific cases, namely n equals 1, 2, 3, and 4, how would you go about proving the general, more abstract case? The thing we need to do is move up a level of abstraction. Say you're given this 2 to the n times 2 to the n board, and we want to fill it up with our L tiles. So we divide it into these 4 equal pieces of 2 to the n times 2 to the n minus 1 subboards. Now the empty square is in one of the subboards. What now? Well, previously we relied on the fact that we finished the work for n minus 1. And the question is, how can we get this reliance now? Well, if we're not done for n minus 1, we can move on to n minus 2 to complete n minus 1. And if we're not done with n minus 2, we can move on to n minus 3 to complete n minus 2. And so on and so forth. We can keep moving down until we reach the number 4. And after that, we can move back up again. Now there's a clean way to write this up, but to do that, we need to know something about the natural numbers. And that thing is the well-ordering principle. It states that in any set of natural numbers, there exists a smallest number. Every such set has a smallest element. So let's look at all the numbers that we can solve and take the smallest such number. Call that number n. We know that this number isn't one of 1, 2, 3, and 4 because we've shown how we tile the board for those values. So n is at least 5. And given it's the smallest such number that we haven't solved, that means we have a solution for n minus 1. Now this solves one of our 4 quadrants. And now, what about the other 3 quadrants? Well, we use that bigger L shape to solve our problem. If we had it, we'd be done. So let's change the numbers we're looking at. Make it the numbers that we can solve, or numbers for which we can tile the L shape that has sides of length 2 to the power of n. Now, if there are natural numbers that are in this set, let's again take the smallest one and call it n. Again, we can solve the quadrant with the missing square by the fact that we know n minus 1 is solvable. And now for the remaining L shape of length 2 to the power of n, we know we can tile it with 4 L shapes of length 2 to the power of n minus 1. And we know that we can tile each of those 4 L shapes with small L shapes. So now this means that there can't be any numbers n for which we can't tile the whole board or the L shape that has a side length of 2 to the power of n. This means that via this process, we'll be able to tile all the natural numbers n. So what happened here? So to sum it up, we first solved a couple of cases showing this thing worked out, namely n equals 1, 2, 3, and 4. Then we assumed that there was some n for which it doesn't work yet, and took the smallest such n. And then we showed that we can make it work for this n. This is the essence of induction. The major difference is in some terminology and approach. In induction, we still have our base cases. In induction, you assume something is true for n minus 1 and prove that, given that assumption, the same thing is true for n. Here we took the smallest n, for which we haven't proved the thing we need to prove, and used the fact that the thing we are proving is already true for n minus 1. I think this assumption part in induction is what's very weird for people when they first learn about induction. It was certainly very weird for me when I learned about it. I did not understand, like, how can you assume that something is true? The use of the word assumption hints that there is something you don't know, whereas what you're really trying to describe is a process for solving a problem when writing an inductive proof. In the next videos, I'll go over more examples of induction applied to combinatorics, number theory, and algebra. Let me know if you have any suggestions, and as always, thanks for problem solving.